Good afternoon. Today we're going to pick up with some of the remaining items we have in preparation for test number 4. And from the second part of the test 4 review, okay, we had left off with a remaining item, okay, and this is the holdover which we had with mathematics of financing concerning annuities. And we have someone who is planning to retire in 15 years. And the plan is calling for $1,000 on a quarterly basis for a time span of 15 years, and we're looking at the rate of return, okay, to be at 10%, okay, where interest will be compounded quarterly. And for parts A and B, A is on the side of what we have with the theoretical minimum balance at the end of the 15 years, whereas in the case of Part B, we're looking at the theoretical maximum. And in the case of annuities, okay, so for what is drawn out in the plan, okay, we're looking at, again, a quarterly contribution of $1,000, and for the rate of interest, okay, we have it 10%, and in looking at the determination of how much the future balance is going to be, especially where interest is compounding, again, we convert from percent to non-percent decimal. Okay, so 10% we're going to have at 0.10, and again for quarterly compounding as well as quarterly contributions, we're going to have that n is equal to 4, and again for the time span, okay, we have for 15 years. And for what we have in Part A, okay, now we're looking at where the contributions will be made at the end of each quarter as opposed to the start of each quarter. So you have a bit of delay in terms of the amount of interest that is being accrued. Okay, so you're looking at the end of every 3 months as opposed to the beginning. And so for what we have on the minimum side, okay, this is again the traditional annuity formula. And we have our known values, okay, for P, R, N, and T. And the unknown is going to be the future value, again, which is going to be at A. And taking what we have with, again, the contribution amount, okay, so we have at $1,000. We have times the quantity, okay, so we have, again, the annuity formula looks like an augmented version of the non-continuous compounding future value algorithm. And for R over N, so R we have at 0.10. Again, N we have on a quarterly basis. And for N times T, so we have 4 times 15. You have our times N over R. Okay, so N we have at 4. We have 0.10. Okay, and so after substituting, okay, we have in terms of the activity, okay, so again we have the contribution amount of $1,000, and for what we have within the brackets, okay, so we have for 1 plus R over N with the numbers, so you have 1 plus 0.025. Now we'll just go ahead and write the sum. We've got 0.10 over 4 is 0.025 added to 1. So this is going to be 1.025. And for N times T, we have 4 times 15, which will be 60. So we have minus 1. And for N over R, we have 4 divided by 0.10. Okay, so this will reduce to a whole number. Okay, and looking at continuing. All right, so we still have some remaining operations inside the brackets. Now we have with 1.025 as the exponential base taken to the 60th degree. Okay, we'll have a number that is going to be slightly under 4.4. We have among the first digits, we have 4.3997. We have minus 1. Then we have times 40. And for what we have in following through, okay, so we got $1,000, and the difference we have in the brackets, and I'll show you a few additional digits. So you got 3.3, 997, 897, we have times 40. So for the plan, okay, the minimum future value, okay, it's going to be right at $135,991.59. All right. Now, for what we have in the case of Part B, okay, we're looking at the theoretical maximum. And for what we have, okay, we're still looking at the same principal rate, frequency, as well as time. Okay, and the difference is going to be where we're looking at the installments done at the start of each quarter in the cycle as opposed to at the end. So you're looking at the accruing of interest, okay, at the start. And this time around, okay, we're still looking at items, okay, from the traditional annuity formula, but for the maximum, okay, you're looking at the traditional annuity formula times the key factor, and that will be in the form of 1 plus R over N. Okay, and okay, so you have 1 plus R over N. So 1 plus 0.10 over 4, and you're looking at that times and everything else we have from Part A. So for what's going to happen is that with the sum, it's going to turn out that what we have in the maximum is going to be 2.5% more than what we have in the minimum. So taking what we have from Part A, if we multiply by 1.025, okay, you're going to be looking at some $3,400 more. And for this balance, we're going to have the maximum to end up right at $139,391.38. Okay, and again, the difference between the maximum and the minimum is going to be the 1 plus R over N portion. All right, now for what we have in the case of the remaining review item, again, this is going back to working with, by and large, okay, exponents and logarithms. And we have for the first page, we're looking at evaluating logarithmic terms and just taking what we have here, okay, and we have with these first parts, again, this is going to revert to our first mentioned logarithmic property where we had the base A logarithm of a to the x is equal to x. And for what we have in the first item, okay, so we got the base 6 logarithm of 6. Okay, and so we already have a match, okay, between the exponential and logarithmic bases. And okay, so you got A is going to be at 6, okay, and in terms of what x will be, okay, well, if you got just 6, well, we just have implicitly that 6 is going to be to the first degree. So base 6 logarithm of 6, same in context as the base 6 logarithm of 6 to the first, and so that is going to be equal to 1. Now, for something that has a little bit of a twist, okay, we're still going to have an expression that can be rewritten where we're going to have the same bases exponentially and logarithmically. And we have, in this one, we have the base 4 logarithm of 1 over 64. Okay, now we got a fraction, and if I were to rewrite 1/64 in terms of base 4, okay, now I got 64 in the denominator, and 64 is both a multiple and an integer power of 4. Okay, so 1/64 is going to be 1 over 4 to the third. And if I look at taking what I have, okay, right now I got 4 to the third, but it's in the reciprocal position. So if I translate the reciprocal of 4 to the third and write directly in terms of base 4, okay, so 1 over a base to a positive power is going to be the same as that base to the negative. And here, the base 4 logarithm of 1/64 is going to be that of 1 over 4 cubed, and 1 over 4 cubed is 4 to the negative 3. And we have in the rewrite, okay, we're going to have the a is equal to 4, while x is at negative 3. And minus 3 is going to be the end result for this term. Now for what we have in the next group, okay, we're looking at still evaluating expressions, okay, and we're still reverting to the base a log of a to the x is equal to x. Now for what we have in the case of the base 5 logarithm of 25, okay, and 25 is both a multiple and an integer power of 5. Okay, so putting this in terms of base a log of a to the x, we have the base 5 logarithm of 5 to the second. So a is at 5, x will be at 2, and with the result at x, turns out that the base 5 logarithm of 25 is equal to 2. And we have for part B, okay, this will be kind of reminiscent of what we had in part B from number 1. Okay, so here we have a base logarithm of a given fraction, okay, whereupon we have the base 2 logarithm of 1 over 32. And so we have the reciprocal of a value that is going to be both a multiple and an integer power of the logarithmic base. And with the logarithmic base at 2, turns out that for 1 over 32, now 32 itself is going to be 2 raised to the 5th. Okay. But I want to express this fraction directly in terms of the exponential base 2. So applying the inverse rule, once again, the reciprocal of 2 to the 5th, okay, that is going to be 2 raised to the negative 5. Okay, so we now have a at 2, x at negative 5. And so we'll have the base 2 logarithm of 1 over 32 is equal to negative 5. And for what we have in the third item, okay, so we're still looking at evaluating expressions. Okay, now we have in part A, we have the base 8 logarithm of 1/8. And again, we have in context now, we got a fraction, and this would be the same as 1 over 8 to the first. And if I write 1/8 directly in terms of base 8, now 1 over 8, or 1 over 8 to the first, is going to be 8 to the negative 1. And so for what we're going to have in this result, the base 8 logarithm of 1/8, okay, this will come out to negative 1. For what we have in the case of part B, okay, now we have a whole number with 81, And the logarithmic base, okay, we have it 3. And in terms of relating 81 to 3. Now 81 is both a multiple of 3 and is also an integer power of 3. So in this case, 81, okay, that is equal to 3 raised to the 4th. Like 3 times 3 is 9, times 3 is 27, and then times the 4th, 3rd, 3. Okay, this will come out to 81. So here we have a is at 3, x is at 4. So the base 3 logarithm of 81 equals 4. Now, for what we have looking at in number 4, again, we have, for these 3 parts, we're looking at missing values. And in the case of what we have for part A, okay, we're looking at the base 9 logarithm of 7 plus the base 9 logarithm of 10 is equal to the base 9 logarithm of the value we're trying to determine. And for what we have in this particular setting, okay, so you have, I'll just work to the side here. Okay, so we're looking at sums and differences of logarithms in this set of exercises. Okay, and for what we have in this case, we have the base 9 log of 7 plus the base 9 logarithm of 10. Okay, now remember, okay, you're going to have a change up between addition and multiplication, and also between subtraction and division. So if we were to look at combining, okay, these 2 base 9 logarithmic terms, the terms are adding, and once we put in terms of a single base 9 logarithmic term, again, addition is going to imply multiplication of the attachments. Okay, so with the attachments at 7 and 10, it's going to turn out that for the sum of these logarithmic terms, we'll end up with the base 9 logarithm of 70. And so 70 is going to be the missing term for part A. Right. Now, in the case of what we have with part B, okay, so we have one, in this we have a difference of terms, okay, and if you see the result already, that's fine, okay, because you can have subtraction to imply division. And see, we have in part B, just to sort of bring this out, okay, and if you see that what the boxed missing value is going to be, okay, that's fine. For some it might be self-evident, others might require a little bit more work. Now I'll do it this way. Okay, say if we have like the missing value, okay, we just have this to be represented by x. Okay, so if I have like the base 4 logarithm of x minus the base 4 logarithm of 5 is equal to the base 4 logarithm of 3/5. Okay, and what I can do here, just kind of bring this down, say if you have like a logarithmic equation, which this is. And what you can do in this particular case, right, so you have base 4 logarithm of x minus the base 4 logarithm of 5, and you can have subtraction to imply division. So in this case, we have the base 4 logarithm of x over 5 is going to be equal to the base 4 logarithm of 3/5. And guess what? Difference of logarithmic terms is going to imply division. So we have with x from a positive base 4 logarithm, that's going to be at the top. 5 from a negative, so that's going to be situated at the bottom. And if you notice, we have single base 4 logarithmic terms, and I can take care of the base 4 log. Okay. And so I can just set the attachments equal to each other. have that x over 5 is equal to 3 over 5. And guess what? We got proportions, and it's going to turn out that we're going to have that x is equal to 3. Okay. So we have for the missing value in this case. All right. And again, base 4 log of 3 minus base 4 log of 5. Again, you have writing as a quotient would come out to 3/5. All right. Now, in what we have for part C, now, so we have the base 6 logarithm of 25 is equal to a term times the base 6 logarithm of 5. Okay. If you notice, okay, 25 is not a multiple or an integer power of 6, but I'm looking at writing from base 6 with the attachment at 25 in terms of where the attachment is going to be at 5. Okay, so we have, in the case of the base 6 logarithm, at 25, okay, and if I convert in terms of where the attachment is going to be at 5, okay, now if I write 25 in terms of the exponential base 5, okay, now 25 is going to be 5 to the second, and again just drawing out a coefficient at the front. So if I have a base, the exponential base, okay, raised to a power, I can rewrite that power as a coefficient. And so this is going to be where we're going to end up with 2 times the base 6 logarithm of 5. And that will be the final result in this case. All right. Now, for what we have in the case of the next set of items, and we're looking at expanding a logarithmic term. And for what we have in the case of number 5, it says to use the properties to expand, okay, the base 10 logarithm of the quantity of z times y to the 9th. And we're looking at expanding, and it says each logarithm should involve only one variable and should not have any exponents. And we have, in the case of number 5, okay, so we're looking at a base 10 logarithm of z times y to the 9th. Okay, and so between the attachments, or should I say between the factors, we have multiplication and breaking up. Okay, so again, multiplication is going to imply addition. So separating z and y to the 9th, then we have the base 10 logarithm of z, and we have plus the base 10 logarithm of y to the 9th. And in terms of making any adjustments, okay, where we have exponents, again, we want to write or express as coefficients. So we have for the final layout, we end up with the base 10 logarithm of z plus 9 times the base 10 logarithm of y. Now, for what we have in case of the next item, okay, for number 6, we're also looking at expanding. And this is going to be sort of a different kind of problem. Okay, we've got a radical, and here in terms of expanding, it says each logarithm should involve only one variable and should not have any radicals or exponents. Okay, so with the way that this radical is laid out, okay, this is a bit of a comparative needle to thread. Okay, so you got z cubed, and we have for the square root of x to the 5th times y. And just bring this over. Okay, so you have the square root of x to the fifth times y. So what this will mean, okay, so you have x to the fifth times y, and the square root of an expression will be that expression raised to the 1/2 power. And looking at what we have now. Okay, so you have a base 10 logarithm. And the numerator, okay, we have a z to the third. Now for x to the fifth y, all raised to the 1/2 power. Okay, there's a bit of a trick to this. Okay, first of all, okay, we have x to the fifth times y. Again, the square root of x to the fifth y is x to the fifth y to the 1/2. Okay, now we have different degrees in x and y. Okay, and taking care of what we have with x and y. Now we got by itself. Now we have x to the fifth. And since we have 1/2 on the outside, we have x to the fifth raised to the 1/2. And for y is going to be raised to the 1/2. And for what we have for a base to a power raised to another power, we're going to be taking the product of the powers. So the square root of x to the fifth, okay, that's going to be x to the 5/2. And we have for the square root of y, again, that's going to be y raised to the 1/2. Okay, so it's a bit of a circuitous route in terms of getting rid of the radical and expressing what we have as non-integer powers. Okay, but here we have in the rewrite, so we have the base 10 log of z cubed all over x to the 5/2 times y to the 1/2. Now looking at separating in terms of adding and subtracting. Okay, so we got 3 factors in the fraction. Okay, so we have 1 in the numerator, 2 in the denominator. And we have for z cubed, okay, this is situated at the top. So this is going to be a positive base 10 logarithmic term. And with x to the 5/2 at the bottom as its own base 10 logarithmic term, this is going to be a negative. So we have minus the base 10 logarithm of x to the 5/2, and with y to the 1/2 also situated in the denominator. Okay, once we remove this from the ratio, that is going to be attached to a negative logarithmic term as well. So we have minus the base 10 logarithm of y to the 1/2. And we have in the follow through. Okay, so for the powers we have, we can rewrite as coefficients. And so we have for the final answer, we have 3 times, okay, the base 10 logarithm of z minus 5/2 times the base 10 logarithm of x, and we have minus 1/2 of the base 10 logarithm of y. Again, just looking at working with logarithms. Okay, and another case of expanding. Okay, and number 7, you have a radical. I don't find this to be quite as tedious as what was in number 6. And if I go ahead and rewrite, okay, removing the radical, let's have another base 10 logarithmic term. Okay, so we have in the numerator, okay, so I have 6 times the quantity. And I have x plus 5, which is to the second. And for the cubic root of x to the 4th, okay, rewriting as a base to a non-integer power. Okay, that's going to be x raised to the 4/3. And looking at carrying over and expanding. Okay, so we have with the terms in the numerator. Okay, so I got 6 as the first term, okay, in the numerator. Okay, so we have as its own base 10 logarithmic term, so we have the base 10 log of 6. Next, I'm going to have with the square of x plus 5, so plus the base 10 logarithm of the quantity of x plus 5 raised to the second, and with x to the 4/3 situated at the bottom. Okay, again, as its own attachment. Okay, this will be part of a negative logarithmic term, so we're going to have minus the base 10 logarithm of x to the 4/3. And just looking at what we have in the follow through. Okay, now 6 is not a multiple or an integer power of 10. And just leaving the expression in exact terms. Okay, the base 10 log of 6 is going to stay. And for the second term, okay, so 2 is going to become a coefficient. So we have 2 times the base 10 logarithm of the quantity of x plus 5. And we have at the end, we're going to have what's going to be minus 4/3 of the base 10 logarithm of x. Okay, so that'll be the final expanded mode for what we have in number 7. Now, for what we have in the case of number 8, okay, this time we're going in the other direction. We're going to be looking at going from expanding to combining. Okay, and for number 8, if we're looking at writing as a single logarithm, okay, so where we have coefficients, we can rewrite as exponents. Okay, and we have a set of base 2 logarithmic terms. Okay, so for the first, we have the base 2 logarithm, and we have of w to the 3rd. And we have next, we have minus what's going to be the base 2 logarithm of y to the 1/5. Then we have plus the base 2 logarithm of x to the 4th. Okay, so I've taken care of the coefficients and have converted to exponents. Now we have with the pluses and the minuses concerned. Okay, so setting the stage in expressing as a single logarithmic term. Okay, so we have with the first, we have w cubed is attached, okay, to a positive base 2 logarithmic term, so this will go to the top. Next we have y to the 5th as part of a negative base 2 logarithm, so this will go on the bottom. And we have the last term x to the 4th, so this stems from a positive base 2 log, so this will go at the top. And so for what we have in the case of the final answer, okay, we have the base 2 logarithm of w cubed x to the 4th all over y to the 1/5. Now, for what we have in the case of the next group, Okay, we're looking at not just logarithmic terms, but logarithmic equations. And for what we have in number 9, we had the base 9 logarithm of x is equal to negative 2. Okay. And whatever I have for x must be positive. Okay, so again, we had the base 9 log of x is equal to negative 2. All right, so we got a single logarithmic term. Okay, and what I can do here, okay, is revert, okay, to our second property of exponents. And again, we had base a log of a to the x is equal to x. And again, we have at the same token, we have the a to the base a log of x is equal to x. So what I can do here is I can convert the left-hand side of the equation to only x. If I treat both sides as powers to which the exponential 9, base 9, will be raised. So you have 9 to the base 9 logarithm of x is equal to 9 to the negative 2. Left-hand side, okay, there will be x, and x is equal to 9 to the negative 2, and there's going to be more work to do. Okay, and it says to simplify your answer as much as possible. And this is kind of like Alex's way of implicitly saying that if you have exponents, go ahead and take care of them. So you got x is equal to 9 to the negative 2, which is true. But if I more explicitly state, okay, just what x will be numerically. Okay, so you're going to be looking at, for 9 to the negative 2, by the inverse rule, okay, 9 to the negative 2 is going to be the reciprocal of 9 squared. Okay, so for 9 to the negative 2, okay, that's going to be the reciprocal of 9 squared. And with 9 squared to 81, and since we're taking the reciprocal of this, x is going to end up as 1 over 81. And 1 over 81 is a small value, but it is nonetheless, okay, a value that is positive. So number 9, okay, we have that x is equal to 1 over 81. Now, for what we have in the case of number 10, okay, so we have a base 4 logarithmic term. And in this one case, we've got the base 4 logarithm of the quantity of 3x minus 8 we have is equal to 1. And again, whatever we have for the attachment, again, this must be positive. I'm just moving this over. Okay, so again, we're back to where we have a single logarithmic term. This time the base is going to be 4, and I can take care of the 3x minus 8, freeing it up from the base 4 logarithmic terminology. So again, I can treat both sides of the equation as powers to which the matching exponential base will be raised. Before I had 9. Now I'm going to have the base to be 4. So now we have 4 to the base 4 logarithm of 3x minus 8 is equal to 4 to the first so we have on the left, okay, we have 3x minus 8, and for 4 to the first, okay, that is 4. So I have a two-step linear equation and adding 8 to both sides. So we have that 3x is equal to 12, and then we have with division by 3. Okay, we're going to have that x is equal to 4, and just double checking. So with x at 4, 3 times 4 is 12, 12 minus 8 is 4, 4 is positive, so the value of 4 for x does fit the bill. Now, with logarithmic terms, now we have with number 11. Okay, now we got -6 times the base 4 logarithm of 5x is equal to -12. And for what we have in the case of 11, okay, so we have -6 times the base 4 logarithm of 5x is equal to -12, and whatever I get for x, it must ensure that the attachment 5x be positive. And what we can do here is that we can sort of simplify this equation, and with the coefficient -6 at the front, I can divide both ends of the equation by -6. And so for what we got now, so you have the base 4 logarithm of 5x, okay, is equal to 2. Alright, so we're back to where we have a single base 4 logarithm of an attachment set equal to a constant. And so I can now take care of the presence of the base 4 logarithm by treating both sides once again as powers to which 4 will be raised, just like what I had with number 10. So we have left-hand side. Okay, so this will be at 5x. We have that 5x is equal to 16. And we have a division by 5. We can say that x is equal to 16/5 for 3.2. Okay, and you can go back and check 5 times 3.2 or 5 times 16/5. This will be 16, and 16 is a positive value. Okay, now for what we have in the case of number 12, okay, so we got in this one. Okay, so we got an equation. Now we have 4 plus the natural logarithm of the quantity of x minus 5, okay, is equal to 3. And so just looking at what we have now, with 4 plus the natural logarithm of the quantity of x minus 5 equal to 3. Okay, so I can isolate the natural logarithmic term Okay, So if I look at taking 4 away from both sides, okay, so I have the natural log of x minus 5, okay, is equal to -1. Okay, so for natural logarithms, okay, so we have a base C logarithm. The quantity of x minus 5 is equal to -1. Okay, and so for x minus 5, okay, we can take care of the presence of the logarithmic base, again, applying the matching exponential base and treating both sides as powers, to which in this case e is going to be raised. So for what we have in the follow through, okay, we have on the left, okay, we have x minus 5. And for what we have in the case of e to the -1, okay, this is going to be a relatively small decimal number. And for this case, okay, we'll have about a little under 0.368. And if I'm looking at adding 5 to both ends, okay, before I get too far ahead, we have for number 12, it says to round your answer to the nearest hundredth. Okay, so that means we'll be looking at rounding to the nearest 2 decimal places. Okay, so we have in the case of x, it's going to be right at 5.3678. And we have to the nearest 2 decimal places. Okay, we have 6's in the hundredths place, and the 7 alongside it signals that that 6 is going to round up, and so to the nearest hundredth we have x to come out to 5.37. Right now, for what we have in working with logarithmic equations, once again, and we've got for number 13, okay, we're looking at in this one, okay, the base 10 logarithm of the quantity of x plus 5 minus the base 10 logarithm of 6 is equal to the base 10 logarithm of x. Okay, so here we have a difference of logarithms. And for what we want to have in this setting, to have a difference of logarithmic terms, and just sort of reminiscent of what we had in the very early stages. Okay, like whenever we looked at, say in the case of the base 4 logarithm of x minus the base 4 logarithm of 5, we're going to compile as a single base 4 logarithmic term, like had the base 4 logarithm of x over 5. And for what we have in the case of 13, combining this time as a base 10 logarithmic entity. Okay, so as a single base 10 logarithmic term, so we have base 10 logarithm of x plus 5, and with 6 stemming from a negative, That's going to be in the denominator. All right, so now we have single base 10 logarithmic terms. Okay, and just kind of reminiscent, like if you have like an exponential equation, so if you have the same base on both sides and they're single terms, you could set the powers equal to each other. Well, on a parallel note, okay, we have the same logarithmic base terms, or same, I should say, like base 10 logarithmic terms on both sides, and I can set the attachments equal to each other. So I'm going to have x plus 5 over 6 is equal to x. Again, for both x and x plus 5. Okay, so these must be positive. Okay, so for x plus 5 over 6 equal to x, so if I multiply both sides of the equation by 6, okay, so we have x plus 5 is equal to 6x. And combining variable terms together. Okay, so we have that 5 is equal to 5x. Okay, and we'll have that 1 is equal to x. And so going back, 1 plus 5 is 6. And x is 1. Both values are positive. And so we're going to have that x is equal to 1. Okay. All right, so just picking up, okay, so you have with 13, okay, so you have x is equal to 1, okay, and then crossing over to what we have in 14, okay, so we have with exponential equations. Okay, so we got 64 is equal to 32 raised to the x minus 4. And this is a sample of what we have, okay, for an equation that's going to share a common base. Okay. So we have in the case 64 equal to 32 raised to the x minus 4. Okay, so I have a common base with 2, and with 64, okay, it's going to be 2 to the 6th, and for 32, 32 is 2 to the 5th, and with 32 to the x minus 4, we have 2 to the 5th raised to the x minus 4. And we have with the power property of exponents. Okay, so again, 64 we have it 2 to the 6th, and for 32 raised to the x minus 4 degree. Okay, so we have 2 raised to the 5 times the quantity of x minus 4. So this would be 2 raised to the 5x minus 20. Okay, so we got single base 2 terms on each side, and now we can set the degrees equal to each other. Okay, so you have that 6 is equal to 5x minus 20. And isolating the x term, okay, so you got 6 plus 20, so that will be 26. Is equal to 5x. And we have with division by 5. And we have the x is equal to 26/5. And you can also express as a decimal where 26/5 is equal to 5.2. Now, what we have in the case of item 15, okay, now we're looking at the exponential base e, and it says, just like the other problem, it says to round to the nearest hundredth, in this case to the nearest 2 decimal places. And for what we have in the case of 15, okay, so we have the exponential base e to the x minus 4 is equal to 4. And what I can do here is I can free up the x minus 4 from the power position if I take the base e logarithm on both sides. And so for what we have on the left, okay, so base e logarithm of e to the x minus 4, so this would be x minus 4. And for the base e logarithm of 4, okay, again, the base e logarithm is going to be a natural logarithm. And for the natural logarithm of 4, okay, we have among the digits, okay, so that is going to be, in this case, right at, let's see, that's going to be, so you have among the first digits, you have right at 1.38629. And for what we have for x, upon adding 4 to both ends, and again, just rounding to the nearest hundredth. Okay, so you have 8 in the hundredths place, and with 6 alongside it, this 6 is going to signal that 8 rounds up. So to the nearest hundredth, in this case, x will come out to 5.39. Okay, now in the crossover, okay, for what we have concerning systems of equations, and we have for the determination of the values of x and y, we'll be looking for those that will satisfy the system, okay, whereupon we have simultaneously that 4x plus 2y is equal to -8, and where we have 3x minus 2y is equal to 29. Okay, and so just taking what we have here for the system. Now we already have additive inverse terms with what we have in y, okay, with both positive and negative y terms. Okay, so you got 2y and -2y, and so we can revert to adding the equations together. So I can set things up where I can go ahead and solve for x, Okay, so we have for this system, okay, so we have positive negative 2y, okay, those will cancel out. And we have 4x plus 3x, so this will make 7x. And we have negative 8 plus 29, okay, so that will make 21. And so we have for x, if 7x is equal to 21, okay, we're going to have that x is equal to 3. Okay. So I have half the solution. Now I need to determine what y is. Okay, and what I can do here is I can plug in 3 for x in either of these two equations and set things up whereupon I can solve for y. So we plug in 3 for x, solve for y. And so what I have here, I'll just go with the first equation. I'm just plugging in for x. Okay, so we have 4 times 3. Plus 2y is equal to negative 8. So we now got 12 plus 2y is equal to negative 8. And taking 12 away from both sides, okay, so we have that 2y is equal to negative 20. And finally we have a division by 2, and we have that y is equal to negative 10. So you got x at 3, y at negative 10. You can go back and check. 4 times 3 is 12. 2 times negative 10 is negative 20. And 12 minus 20 is equal to negative 8. And we have with the second equation, 3 times 3 is 9. Negative 2 times negative 10 is a positive 20. 9 added to positive 20 comes out to 29. And so we're going to have for the solution, okay, we have x is equal to 3, and y is equal to negative 10, and just writing as an ordered pair. So there's only one point of intersection between the graphs of these equations. Again, that point is going to be located at 3, negative 10. Then we have for number 18. Now I just mentioned, okay, now 17, that problem is from a different section. It's section 8.2. We won't be dealing with this. But for 18, okay, there is a blend of linear and nonlinear equations. And for 18, we're looking at solving for x and y such that we have that y is equal to x squared minus 8x plus 2. And I'll say that y is equal to negative 2x plus 18. Okay, and so for what we have in the system, okay, we have a quadratic function as well as a linear function. So for what we have here, okay, we don't have things aligned. Oops. Okay, we don't have things aligned such that we can conveniently use the method of addition. Okay, and plus we don't have the same degree in x in the equations. Okay, but what we can do in creating a pathway to solving for y, Instead, we can use the other method. Other than the method of addition, or some might call it elimination, we have the method of substitution. Okay, so again, both equations are in terms of y. Okay, so y is equal to x squared minus 8x plus 2. We have also that y is equal to negative 2x plus 18. Okay, and with substitution, okay, now the variable we have isolated, in this case y, we can substitute for in the other equation. Okay, so like for the first equation, we got y defined in terms of x as being x squared minus 8x plus 2. And if I take this trinomial and substitute for y in the other equation, we'll have the other equation in terms of the variable x, where I can go ahead and solve for the letter x. Okay, so looking at substituting for y and solving for x, so we'll have in the rewrite, okay, so I have x squared minus 8x plus 2 is equal to negative 2x plus 18. Okay, so I have a quadratic equation, and what I can do is I can set this up as a quadratic equation in standard form. Okay, so setting the equation to 0, so I'll just move the 2x and the 18 by respectively adding and subtracting. So here I'm going to have x squared minus 6x minus 16 is equal to 0. And the trinomial I can factor, and with the terms, okay, so I have x plus 2 and x minus 8, and with the use of the zero product property, setting each of the factors to 0. So if x plus 2 is equal to 0, we have x is equal to negative 2, and when x minus 8 is equal to 0, so we'll have that x is equal to 8, right? And for what we have in the setup, okay, now we got equations of different degrees in x. And in terms of what to do, in terms of the strategy to utilize in solving for y, okay, and just kind of a heuristic. Whenever you're looking at solving for the other variable, use the simplest equation, simpler or simplest. That is like the lowest degree equation. So it's kind of like with this system. Okay, if you notice, you had first equation had like squaring x, second equation had both x and y are first degree, so that would be regarded as the simpler equation. Okay, so in this case, for this instance, we have that y is equal to negative 2x plus 18. Okay, so when x is equal to -2 for the corresponding value in y. So again, utilizing y is equal to -2x plus 18 and -2 times -2 plus 18. -2 times -2 is 4 plus 18 is equal to 22. So that is for one set. And whenever x is equal to +8, and y is equal to -2x plus 18 once again, this time with x at 8. So that -2 times 8 is -16. And -16 plus 18 is equal to 2. Okay, so we have a couple of pairs of values here, and so for what you're going to have in terms of the solution, we'll have two distinct points here. We have for x and y. Okay, so one ordered pair solution, we have x equal to -2 and y is equal to 22, and also in the other scenario we have that x is equal to 8 while y is equal to 2.